Once again, here's a load shear moment diagram problem. You're given a beam with a known load situation and asked to draw the diagram. The concept here is that we'll come up with a couple of different sets of equations that we can just plug in an x value for and find the value of the shear force or the load force or the moment at that particular location. The first step is to draw a free body diagram of the entire beam and solve for support reactions. So I've skipped a couple steps for sake of time, but here you can see what I've done. I took each of these shapes, these distributed loads were each a triangle. The area of a triangle is 1/2 base times height, so the value of the force that replaces each one is 9 kilonewtons. That's 1/2 base times height. The force is located 1/3 of the base away from the side with the right angle, so that's d distance away for L2 and c distance away for L1. I then solve for support reactions independently using some of the forces in the x for ax, some of the moments around point B for ay, and some of the moments around point A for by. After I found all the support reactions, now I can begin to break the original diagram into sections. So now here's our first section free body diagram. You'll notice that I've replaced the unknown hinge with two known forces, ax and ay. Make sure that their senses are actually correct. So if I would have gotten a negative for ay, it would need to go down. Also notice that I wrote on the distributed load the equation for that line. It has an intercept of +6. Remember, our 0, 0 is always here at the far left, and its slope is -2. How do I know that? The rise is 6, the run is 3, and it's going down. So 6/3 is 2, and it's in the negative direction. I still encourage you to plug the values in. So if we plug in 0 for x, that's over here, we get 6. And if we plug in 3 for x, we get 0, and this does indeed taper off to 0 at 3 meters. The length of this section is x. The length of your sections when you draw them will always be x. In this case, x is greater than 0, but it's less than 3, so it's before that distributed load comes down to a point. Now we need to apply our unknowns, which are our axial force, our shear force, and our moment. And those will have to be applied to this diagram with the senses correct based on the designer's sign convention. So recall that P, the axial force, must stretch this section, so it is indeed doing that. V, the shear force, has to produce clockwise rotation around the other side of the beam, which it does, and the moment has to compress the top fibers of the beam, which it is also doing. So now we're going to solve for these internal forces, and we're going to solve for these just like we've solved for anything else using static equilibrium. In order to solve for P1, I'm going to sum forces in the x direction. Since ax is 0, that leaves me with P1 as 0 kilonewtons. In order to solve for V1 independently, I will need to apply static equilibrium to the y direction. Now, in the y direction, we have ay and V1. We also have this distributed load up here. Now, this distributed load is actually a compound shape. I want you to notice, since we've cut it just short of being a triangle, we actually have two shapes. We have this shape, which is a triangle, and we also have this shape, which is a rectangle. So the area for a rectangle is base times height. The base of this rectangle is x. The height of this rectangle would be this point right here, which is dl. So that takes care of the area of the rectangle. Remember, we need that area because the value of the force that replaces the distributed load is equivalent to its area. Now we also need to account for the triangle. The triangle is sitting on top. The area of a triangle is 1/2 times base, which is x, times the height of that triangle. Now the height of that triangle is not 6. 6 is this point over here, and it's not dl, which is this point over here, but rather it's 6 minus dl. So now we can simplify this equation. Now we can start to plug numbers in. This is a perfectly acceptable way to report this particular equation. You'll notice it's not a single answer, but it's an equation for v as a function of x. However, I always like to reduce these, and combine like terms and simplify them. So if you do that, you will get this. Now I want to point out that you can also get this shear equation by integrating the equation for the distributed load between its limits, which its limits are 0 meters and 3 meters. That equation dl1 is valid between 0 meters and 3 meters. Likewise, the equation for v1 is only valid between 0 meters and 3 meters. So anywhere in there you can plug in a value for x and find what the shear is going to be. I know that this equation is a little tricky looking. I just want to reemphasize that we're still just using static equilibrium. The only thing that's tricky about this equation is these x times dl. These are areas of the distributed load. So x times dl1, that's the area of the rectangle for the distributed load. X over 2 times 6 minus dl1, that's the area for the triangle. Finally, for this section, we're going to find the bending moment 1. In order to do this, we're going to apply moments around point O. Point O is not the origin, it's this point here on the right side of the beam. And doing so will cancel out V1 and P1, leaving the only unknown as BM1. So we will have AY times D perpendicular, the moment itself. Remember, x times dl1, that's the value for the area of the rectangle at the bottom of this distributed load. We need to multiply that force by its perpendicular distance. And in this 1/2 x times 6 minus dl1, that is the area of the triangle at the top, which would be a single point force. And then we have d perpendicular here. Now x times dl1, that is the area of the rectangle, and that force would be located at the center of the rectangle, at its centroid, which is right in the middle. So that's going to be x over 2. And this last perpendicular distance, remember, the triangle's area is 1/2 base times height, and its centroid, where that force will be located, is 1/3 away from the side with the right angle. So that would be x minus x over 3. Another way to write that would be 2/3 of x. Solving this equation for BM1 gives this, and now we can plug our numbers in. Once again, this is a perfectly acceptable way to end this, but because I prefer to reduce the equations, I go ahead and reduce it down and combine all like terms. If you do that, this is what you will end up with. And that equation right there is what you would get if you take the shear equation and you integrate it. So now I've drawn a new free body diagram, and this is required whenever you have a discontinuous distributed load or if you have forces disrupting the distributed load. So in this case, I have two distributed loads and I cannot accurately represent them with one single equation, so I have to have two different diagrams. That would be the case in the first example I showed you with the point forces. If you wanted to write equations, you would have had to write a set of discontinuous equations. In this case, I have to because the distributed load is discontinuous. So if there are point forces acting on the beam while there's distributed load, or if there's a moment somewhere in the middle, that's when you would have to do this. You'd have to make multiple free body diagrams. In this case, my first free body diagram was immediately before 3 meters, between 0 and 3 meters. This second free body diagram is past the 3 meter mark, but not quite to the end. We're cutting it just short. And you'll see I have my equation for the second distributed load written up here. Now, if you'll notice, I have replaced the first distributed load with L. It's much simpler that way, and I can do so because the entirety of that distributed load is taken up in this section. The total length of this section is always x, and x always starts at the far left of the beam. In this case, I'm going to find a set of equations for my distributed load, my shear force, and my moment that are valid between 3 meters and 6 meters. The first thing to do is apply my shear force, my axial force, and my moment here at this new point Q. So here you can see my axial force stretches this section, my shear force produces clockwise rotation, and my moment compresses the top fibers of the beam. Now we can again apply static equilibrium to the x, the y directions, and to moments around that point. This equation is somewhat simpler. Whereas before, when we cut off the beam just before 3 meters, we had a triangle stacked on top of a rectangle. Regardless of how long this section is, this shape over here will always be a triangle. And the value for the area of a triangle is 1/2 base times height. So this triangle is 1/2. Now be careful here. The base is not x. X is the total length of the beam. Instead here, the base is x minus a. The height of this triangle is dl2. Now that I've solved for v2, I can plug the numbers in. And I'm going to go ahead and simplify this once more. And there's the equation for my shear force. In order to independently solve for BM2, I'm going to sum moments around point Q. Notice I'm not including P2, V2, or AX in this equation because none of those produce a moment around point Q. Now remember that the force that replaces the distributed load is equivalent to its area, and it's located at the centroid. In this case, that force is going to be right about here. The area is 1/2 times x minus a times dl2. It would be 1/3 away from point Q, which means it's the base, which is x minus a times 1/3. Now we can solve this equation for BM2, and now we can plug our numbers in. And there's the final equation simplified. Now there's sort of 3 categories of people out there. There's someone who doesn't know any calculus at all, someone who's only vaguely familiar with calculus, and someone who's much more comfortable with calculus. Here's what I would say to each of you. First of all, if you don't know any calculus at all, you can completely ignore the calculus. You can do it using this algebraic method I'm showing you here. However, I do want you to know that this is actually integrating. Between the shear equation and the moment equation, all we're doing is we're integrating that. To the second group of people who maybe have a basic understanding of calculus but aren't really very comfortable with it, what I would encourage you to do is I would encourage you to solve it using this method and then use the integral to check your answer. If you do your math right, the integral will be exactly the same as this equation here. To the third group of people, I would say if you're very familiar with the calculus is a much faster way to solve this, and I encourage you to do that if you feel comfortable doing so. The only thing I need to point out about integrating is that this equation up here, the distributed load, is shown as a positive 2x minus 6, and it's going down. Typically in engineering setting, when we draw these diagrams, we draw the loads on top of the beams. However, when you look at the shear equation for this section was negative 2x plus 6x minus 9. So it looks like the signs all flipped. Integration does not flip signs. What actually is going on here is although we draw the load on top of the beam, it's going in the negative direction. So really this equation is actually down here, and it should be negative 2x plus 6. That said, however, this is kind of the standard way that we represent it. So if you're integrating, just realize that on your first integration step between the distributed load and the shear equation, you're going to have to flip the signs. That doesn't happen between the shear equation and the moment equation because the signs are already taken care of there. So when we come to the load shear moment diagram, the initial diagram once again is just the original free body diagram, with all of the distributed loads, external moments, and external forces applied on it, along with the distances and values. I do want to see the equations for the distributed load, for the shear, and for the moment written above each section. Now, there's a couple of ways to do this graph. If you have a graphing calculator, feel free to punch these equations in, and you're going to see the equations graphed. A graphing calculator is definitely not required for this, but it is helpful. If you don't have a graphing calculator, you can still pretty easily figure out what's going on. So in this first section, initially, we have a point force at point A, which immediately forces the shear diagram up positive in the positive direction by that amount. After that, the shear diagram then tapers off to 0. Now, if you look at your equation, it's 9 minus 6x plus x squared. So since it's a positive x squared, this particular parabola will be concave up. And you can just plug a couple of points in to figure out what the values of those are if you need to do so. And you can see that in that equation, if you plug 3 into that equation, you're going to get 0. On the other side here, we also have another parabola. However, it's negative x squared plus 6x minus 9. So it's exactly the opposite of this. It's going to be concave down. And just like before, when we get to the other side, if you plug in 6 to this equation, you're going to get negative 9. This by force immediately pushes it back to 0, so it starts and ends at 0. Now I do want to point out that these are just sections of each of these curves. So v1, for example, 9 minus 6x plus x squared is an entire parabola. However, the only values on that parabola that are valid are those between 0 and 3 meters. Likewise, the only values on the second parabola that are valid for this problem are those between 3 meters and 6 meters. For the moment diagram, we can first plot this equation, which is a cubic function, and only this portion of it is valid between 0 and 3 meters. It ends at a positive 9. That's the height right here at the middle. The second equation is 18 minus 9x plus 3x squared minus x third over 3. If you plug 3 meters into this equation, you'll get 9. If you plug 6 meters into this equation, you'll get 0. And those correspond with the starting and ending points on the moment diagram. One last thing I want to note, just a quick check. You will see that the load diagram has a power of x to the 1. The shear diagram in this case has a power of x squared, and the moment diagram has a power of x to the 3rd. That is the case. Your x will increase by a factor of 1. The power of x, that is, will increase by a factor of 1 every time you do this.